Go.
Shall I start?
Yes, please.
Okay, great. Okay, let me start, of course, by thanking you, the organizers, for inviting me to present this work here at this workshop. So the workshop contains a few keywords. My talk is gonna tick the boxes for holography and BPS, not anything about quantum information, but we'll see how it goes. The main focus of this talk is a paper which is being finalized. In fact, probably two. There'll be two companion papers that should appear probably in September, but you never know. And the co-authors are Jerome and James, as well as Andrea Boido, who is a student of James Parks in Oxford. All right. All right. So that's the outline. So I will. The first part will be kind of recalling some of the introductory part. Let's say recalling some of the developments that occurred in the past couple of years about some constructions of branes and supergravity solutions, which involve this object called spindles, which are some orbifolds, which I will mention. And then the second part will be devoted to the results of these upcoming papers, which hopefully I'll be able to explain a bit. Right. So the motivations are the main motivation which we can have in mind. The setup is a bit broader, but we can have in mind as motivation that of understanding supersymmetric black holes in the context of holography, and therefore, in particular, black holes in anti-de Sitter space. And our main focus will be in ADS4, as we will see. So once we have a black hole in ADS, from the conformal boundary data, we can read off precisely the dual quantum field theory and the background where it lives. Therefore, we can make very precise checks, very detailed checks of the ADS CFT correspondence. So for this reason, this is one of the most useful approaches for improving our understanding of quantum gravity using holography, as has been mentioned already in various talks by Lars and other people. The main object, concretely, that it's useful in this comparison and will be the like our target somehow, is the entropy function. So we can define the entropy function in two different ways, which are summarized by these diagrams. So if we start from a black hole, which we take to be supersymmetric, and we compute, for example, the on-shell action, then this gives an object which, once we extremize, will produce the entropy of the black hole. It is even clearer if we follow the field theory path. So we compute the field theory dual, we put it on some background, we compute the partition function, for example, doing localization, and then we take the Largen limit to match the regime of the supergravity. And from there, we can, taking the logarithm of this partition function, again, we have an object. Once we extremize, it gives the entropy. So this object is called the entropy function. It's somehow a function that encodes a lot of information of the black hole. So general fact is that any supersymmetric black hole in any dimension, in fact, and with any boundary condition, in the near horizon region will approach anti-de Sitter 2 times horizon, which, for example, in 4-dimension well-known horizons are Riemann surfaces of constant curvatures of arbitrary genus, and in 5 dimensions, for example, we can have a S3. At least for the case of spherical horizons, so when there is a sphere, S2, S3, etc., the black hole can rotate, of course, so they can have angular momentum, and therefore this product here is really a twisted product somehow. There are some mixture, but I would refer it generically as a product. And in fact, a lot of what I'll say later will be for the case where there is no rotation. In 4 dimensions, which we can focus on, there are two known, at least until a couple of years ago, there were two known ways to preserve supersymmetry. One is the well-known topological twist, where we identify the spin connection with the background gauge field, which I will refer to as AR. So it's a gauge field for the R symmetry, therefore the R. And in the rotating case, so where you have spheres, then we have the usual killing spinors on spheres, which are well known. Essentially, in this case, there is no twist. Okay, so the basically this condition, I can refer it as no twist, this condition will become a bit more interesting when we have more than one gauge fields. Okay, so although the topologically twisted one were first studied by Benin and collaborators, I will jump to the rotating case, which is for me more interesting for the generalization which I have in mind. So let me start in the context of four-dimensional gauge supergravity. We can take as so-called STU gauge supergravity. So there are the gauge group is U1 to the fourth. There are four gauge fields in this supergravity, and associated to this gauge field there are electric EI and magnetic charges. I will refer to electric charges and magnetic fluxes. And the magnetic fluxes in general we want to quantize. And then, as I said, this no twist condition imposed by supersymmetry, it means a constraint here on these magnetic fluxes, which have to sum up to zero. Okay, you have if you have such a black hole in this theory, then the entropy, which is in this case just the Beckstein-Hawking entropy, one compute from the horizon, the area of the horizon, so A divided by 4. Is given by an expression that depends on the electric charges E and magnetic fluxes N, and that's the expression. Okay, so there is this square root. Now, the same entropy that you can compute just computing the volume of the horizon can also be obtained by extremizing a function. So this is the entropy function in this case. As I said, it's a main object in our talk here. So this entropy function it contains two terms. There is a term here which I denote by this curly epsilon function. It's quadratic both in the magnetic fluxes and I, as well as in these chemical potentials, phi1 and phi2, and then there is this additional linear term, which is essentially implementing a Legendre transformation. And that's specific to the fact that there is an angular momentum J and electric charges E1 and E2. Okay, so you take this function curly S, and if you extremize with respect to phi and epsilon, subject to this constraint here, then you reproduce exactly this function here. Okay, so these are the critical points. That's the value of the entropy. So we have to distinguish between entropy and entropy function. The entropy is a function only of the charges. The entropy function is a function also of the chemical potentials. Okay. Now, a little warning about numerical factors. These factors of 2 here and half, etc. They vary quite a bit between different literature, even between our own papers. Sometimes they have slightly different conventions. So let's not focus too much on these factors, but more on the idea that there is a linear constraint between these chemical potentials. So here in these slides, I introduced my one of the main novelties that was introduced already almost 2 years ago. Which is this object, the orbifold called spindle. It means that the way I introduced it here, I can replace this sphere, so that the usual horizon, which is spherical S2, with this orbifold, which is a two-sphere with two orbifold points at the north and south pole. Okay, so simply take the sphere if you want and replace the at the north and south poles with these orbifold singularities, but this comes at a price. You can't just quotient by global n quotient, but you have to also deform the metric, because in order to have n plus and n minus different, you can't have just a quotient of the round metric. The magnetic flux is also changed, and instead of being 0 here, the sum of the magnetic fluxes, instead of being 0, they sum up to this object here, 1 over n minus 1 over n plus, which is in general different from 0. And this mismatch between n plus and n minus, one can also interpret in terms of acceleration of the black hole. So if we were to study the full black hole, which I won't discuss much today, I will focus more on the near horizon. But in the full black hole, really this this mismatch is has to do with physically with the acceleration of the black hole. This was previously known only minimal in the minimal theory, and then we had an extension in this paper here with the students. In this case, in fact, different from the Kerr-Newman solution, we can also set the angular momentum to 0. So although we started from there with angular momentum for convenience, once we have the spindle, we can also set the angular momentum to 0. So we can have a static, purely static black hole, which is supersymmetric and which has ADS2 times the spindle as a near horizon.
Sorry, so Dario, so you can start with a Neumann black hole, for example. You can just start with instead of a Kerr-Newman, you can start with a Reisen-Nordstrom black hole. Can you undo this?
The Reisen not well, yeah, you can think. I mean, also
could you start with J equal to 0 and do this straight away?
Yeah, I guess in ADS4 there isn't such an object.
Oh, I see. You're doing ADS4. So sorry.
Yeah.
Okay. Fine,
yeah,
fine.
That's the only subtlety. But in principle, you could have done that, but just in ADS4, you can't have a static supersim and extremal supersymmetric. But in print, morally, yes. For this solution, which we wrote down and discussed in detail, then in this late subsequent paper with Davide Cassani, we studied the thermodynamics of the solution. And here, by thermodynamics, I mean both the finite temperature as well as the extremal limit. So there is a way which I'm not discussing today to approach the basically the supersymmetric case from the finite temperature one, which is quite useful. So the finite temperature is like a kind of regularization that we use, and in this case we can indeed well, first of all, we can compute the entropy, for example, but just by computing again the horizon area, and you see that the spindle data or orbifold data, which I always call n minus and n plus, enter in the entropy, right? So this formula for the entropy generalizes that of the Kerr-Newman through this Euler character of the spindle chi. And the same entropy can also be obtained by taking a Legendre transform, namely extremizing this entropy function, which is in this case, I want to emphasize this point. In this case, the entropy function is really computed from the on-shell action. Many times you will find these entropy functions which are basically conjecture or just kind of given as ad hoc, right? People can identify, basically guess. It's always, it's often possible to guess an entropy function. In this case, there is no guess. We really compute the on-shell action with this delicate procedure of regularizing with the finite temperature. Anyway, let's go now to the next step. The next step that that we have to do in order to get to our main focus is to uplift the solution from 4 dimensions to 11 dimensions. Okay, so that's important. I want to emphasize this point because everything which I will say from now on will not be in the gauge supergravity, but we will work directly in 11-dimensional supergravity, or in fact we will see that there is a parallel also with the story in type 2b. So, but in any case, let's say we work in string theory. Right, so we take this solution, we can uplift it, and then the solution uplifted look like some M4 times a Sasaki-Einstein manifold. Also, the solution with more charges. So this is the case of the minimal theory. The solution of in the STU theory can be uplifted, in fact, just on S7. So the uplifting solution are known only in S7. And when I say this. Again, these products are actually fibration. We have the Sasaki-Einstein or the S7 are fibered over the internal, over the lower dimensional ADS2 times spindle solution. And at this point, right? At this point, we have an ADS2 times some big, well, 9-dimensional manifold. in 11 dimension, and we can interpret that solution. We could have just started from here. Okay, I give you a solution which is ADS2 times something, and this is interpreted as arising from wrapping n and two branes on the spindle, so obtaining an effective one-dimensional theory from the M2 branes, and this one-dimensional theory is conformal and therefore has an ADS2 factor in the geometry. How about the internal part, the 9-dimensional part? Okay, the 9-dimensional part, as I mentioned already here, is a fibration. The Sasaki-Einstein-Savelle manifold is fibered over the spindle. So you have you basically ADS2 you can factor out and forget about it, and you have this spindle which is this little orbifold with the Sasaki-Einstein which is fibered over it, and this full Y9 geometry now. We are in good shape because it belongs to a class of solutions which have been studied originally in a paper by Kim and Park, and later in a paper by Gauntlet and Kim, and we refer therefore to these geometries as GK geometry. Okay, so I will refer to the full 9-dimensional geometry as GK geometry, and as I said, from now on we will also set always J equal to 0. It's an interesting generalization that can be done in principle, but we have not done that yet.
Can I ask you a question here?
Sure.
Can I ask you a question? These JK
sure.
geometries.
Yeah.
Are you saying that if one would have started with a JK geometry, one would have naturally been led to the concept of a spindle solution?
Well, I don't know if naturally or not, but eventually you would have led to that. Yes. In fact, there is even more. In fact, some of these solutions, which I will never write any magic explicitly. So there are some explicit examples, but my philosophy is that actually we want to do work that is independent of the explicit solution. So that's why I never write a solution. But many solutions were found of these. So let's say there are explicit examples of this GK geometry, and you can find them in the papers, but you will never, say of 10 years ago, but you will never find the spindle, not even not even with a different name. So it was not realized that in fact these 9-dimensional solutions contain in their belly already the spindle. It's like we realized that a posteriori.
Okay, thanks.
But yeah, you could have one could have found those spindle from those solutions indeed. Now here is kind of a little parenthetic comment for this talk today, but it would give rise to other types of talks. One can replace them to brane in this construction. Also, so when I mean construction, I mean in the wrapping on the spindle with different kind of branes, basically, well, almost every kind of branes, and these are in kind of chronological order. D3, M5, D4, D2 branes. All of these cases have been studied by different people, many of these cases by myself with my collaborators, but also other collaborations. And there is kind of a pattern, the ADS2 times spindle solution that I discussed in kind of a detail quote marks. They are replaced by ADS-P with the spindle in different gauge supergravities. So for example, you pick, I don't know, P equal 4 if you want, then you get ADS4 times spindle, and this corresponds to the 4 branes wrapped on the spindle, and so on. And in each of these cases here of this line, you can these solutions can all be uplifted to their pertinent higher dimensional theory. So this is type 2b or massive type 2a or even natural supergravity and so on. Okay, so I could talk about any of these examples, but some of the details differ. Well, many details differ if we consider M2, M5, and D4. So I will not talk about those cases today. Instead, I can discuss M2 and D3 in parallel, because they are basically the same kind of GK geometry, just in different dimension. Okay, so there is, as I wrote here, this kind of minor dimension dependent factors that appear, but it's the same geometry that characterizes solutions of type 2b arising from D3 branes wrapped, and also solutions in 11 dimension arising from M2 branes wrapped. Okay, so that's going to be the focus later on. Just another couple of information about the spindle itself. So in order to wrap the brane on a spindle, well, we have to give a metric, and this metric, as I already alluded to, it's not constant curvature, so it's a metric that we have to find by solving the Killing-Spinor equation. But as a general fact, which is kind of a global fact, it's not just the detail of how the solution looks like. There are in fact only two ways to preserve supersymmetry. Okay, so this is exhaustive. It's like one can prove in general just by using general arguments about the spin structure on the spindle, etc., that there are two ways that one can preserve supersymmetry. One is the one that which already appeared in the example that I mentioned as my introduction, and we call it anti-twist because there is a minus sign appearing, and this minus sign is kind of the opposite sign of what appears in this case, which we call twist, which is a straight generalization of the topological twist. Right. So this appears in the next line. So if you imagine setting removing the conical singularities, so going back to the sphere. So it means you set n plus n minus equal to 1, right? So you get the two sphere. The second line reduces to the ordinary topological twist on the sphere. You can check that by plugging g equals 0 in the genus formula. And in the first line, you get 0, which is this no twist case. Okay. Now, a notation that we use in some of our papers in order to kind of spare formulas, we use a symbol sigma, which is either plus or minus 1. So it's a sign. For example, in these two formula, we would write it as a single formula with the sigma in the middle. Okay. So we can treat both kind of twist with this at the same time. It's important to bear in mind that by definition, n plus and n minus are positive, so you can't just change the sign of them. And also we take them co-prime. Being not co-prime brings additional complications. Another thing I want to mention is that, and that has to do with this entropy function, which we are going towards, is that this entropy function actually can be defined and extended to all these cases which I mentioned when I said M2, D3, D4, M5, etc. So in this paper last year with Federico Faedo, we proposed a general formula for this entropy function, which if we are not in ADS2, we don't call them entropy functions because, for example, if you are ADS3, then there is the dual is two-dimensional CFT, etc. Right? So we call them off-shell free energies. Okay, but they're kind of higher dimensional extension of the notion of entropy function. So essentially, it's the same object. It's a function that once you extremise, it gives the corresponding physical observable. So for ADS2, one-dimensional CFT, that is the entropy, but for example, for ADS3, two-dimensional CFT, that is the central charge. Right. So in any dimension, you have a corresponding observable. Let me mention, for example, if you are in 3 dimensions, then you have the free energy of the corresponding theory, etc. So we gave this with this formula, which, as I also said earlier, in this case it's a conjecture, right? So this formula coincides with the previous formula. Let me just flash it because just for clarity. So this formula here, which I told you earlier, and which is computed from the on-shell action, it's basically the only case in these general formulas where it's proved so far, and the other are all generalizations which are conjectural. We expect it should work in this way, and in fact we have some checks that if we actually take these entropy functions and do extremise them, you always reproduce the correct object. So this function here has to be accompanied with the 2 additional equations. One is the constraint among the chemical potentials, and again, this generalizes the one that we proved in the case of the solution that we constructed, and this constraint between the magnetic fluxes. Okay, so this formula here reduces also to the anomaly and polynomial computation. So there is already some checks for the case of D3 and M5, whereas for the case of M2 and D4 branes, which are field theories in odd dimensions, the field theory story is behind. So there we have to do the local. I mean, someone. I'm working on that as well, but eventually someone has to do the localization on the spindle. Okay, so that's another. Again, it's a different topic for a different talk, but it's a very interesting also direction. Okay, so here, well, I should have emphasized already, but I will do it now. The important point of this formula is that it takes the formula or the form of a sum of two terms. Okay, never mind this relative sign, which is something which I will not discuss much. But there is this form of a sum, which in terms of if you consider the exponential of those, so where it comes from, the partition function, it's kind of a factorization. So sometimes this formula also is referred to as factorization, or as the composition in blocks, and these blocks are called gravitational blocks from papers by Alberto Zaffaroni et al. And specifically these curly F D blocks, D is the dimension dependent factor. I can give you a table with all these explicit functions. Okay, so that's the relevant line to look at is this one, the second line. And in any dimension, for example, let's say we are in 4 dimensions, so we let's say super Young n equal 4 super Young mills, to be very concrete, right? So this formula here, this cubic in the chemical potential is the off shell trial central charge of the dual 4-dimensional theory, and it appears with different factors and different roots for the different dimensions. Okay, so one thing I want to draw your attention to is that in all these cases here in this table, the parent theories, so those that we're starting from, say n equal 4 super Young mills or ABJM, they are dual to ADS. Here I intentionally didn't put any dimension, so depending on which theory I'm talking about, like ABJM, this would be ADS 4 times S7 and so on. Okay, so this is kind of a under control and with some partial checks for the sphere. Later on, I will well, one of our main results will be that we can generalize this block formula to cases where we don't have to restrict to theories which have spheres as duals. Okay, so here is the let's say we are kind of in the middle point of the talk, more or less, and here is the question: can we prove this conjecture, right? So this is the conjecture in the box. The conjecture is that the entropy function, it's written as a sum of 2 blocks, and these blocks are associated with the observables of the parent theories. And the question is, can we prove this conjecture? And the answer to this question is in the upcoming papers. And as I said, for M2 branes and D3 branes, we have proved this. So we have proved this gravitational block formula employing the GK geometry, which I will next I will remind you or explain to you what is this GK geometry. So it means that we are working directly in 10 or 11 dimensions, and our results in principle cover all the supersymmetric solutions with ADS3 and ADS2 factors. So they don't cover one example or 2 or 10, but in principle, all the solutions that they contain just an ADS3 and ADS2 factor, and the internal geometry is in principle completely arbitrary as long as the solution is supersymmetric. So the point, I mean, the takeaway point of this, the takeaway message of my talk, one of those, is that we want to obtain information about the solutions without explicitly solving the Einstein equations. Okay, so as we will see, in some cases, as I mentioned already, one can find examples, but in general, it's hopeless that one can imagine that you would find all possible solutions in explicit form. Right, so as you decrease the symmetry, there will be less and will be harder and harder, and we already expect. I mean, we clearly expect that it won't be possible to find all solutions, but we would be able to extract information also for these cases. So I will start by flashing some formulas specifically in 10 dimension, but as I mentioned, the 10 or 11 dimension, it just there is some just factor. I will introduce some n, which will be then say n equal 3 or 4, and we'll cover both cases. Okay, so for concreteness, let me write this formula here for ADS3 times Y7. Maybe I should have done ADS2 times Y9, but anyway, it's, as I said, they are basically almost identical. So there is a metric which is contains an ADS3 factor and an arbitrary internal 7-dimensional metric, and then there is a phi from flux, which is entirely encoded in this 2 form f, which is closed and defined on Y7. So the data of the solution are this function b and this 2 form f and the metric, let's say. And for any consistent solution, we also must impose the flux quantization condition, which for in this case in type 2b, we have to quantize f5 through any 5 cycle which enter in the 7-dimensional part of the space. Now, the next thing is that we impose 0,2 supersymmetry, and that this comment ties in with what we discussed yesterday when Alejandro was there. So in principle, one could also look at what happens if you have 2,2 or other fractions, and there are indeed papers which have done that, but we impose this, right? So we just see the structure which is generic to 0,2, and importantly, the reason why we impose 0,2 is that we want there to be an R symmetry, which is a U1 R symmetry, and therefore there is in the geometry there will be an associated Killing vector. Right. So if we had 0,1, there wouldn't be an R symmetry, and so there wouldn't be any Killing vector. Right. So this presence of the Killing vector imposes that the 7-dimensional space actually has this structure. There is a transverse space which is 6-dimensional, and there is a 1 form which is dual to this Killing vector. Right. Z is a coordinate, and as further data. The fact that the transverse 6-dimensional metric is scalar with scalar form J and Ricci form rho. Please interrupt me if you want me to kind of, I mean, if you want anything to be clarified, I can always keep material at the end, so I don't mind. And then, for example, the 2 form F, which I said it's a data, becomes related to the completely to the geometry of the 7-dimensional space through this formula. You can see J appears here, the scalar 2 form, as well as this 1 form eta. And also the scalar e to the b is related to the Ricci scalar of the geometry. Now, finally, there is a last tiny bit, but it's a very non-trivial bit. If we want to have a full solution of the equation of motion, we also have to impose the Bianchi identity, and this we refer to as going on shell. And this apparently humble imposition, in fact, leads to this very non-trivial equation that you have to satisfy, right? So you can't take any scalar metric. You can't take, say, metric on CP3 or whatever you want, but you have to satisfy this equation here, and that's kind of the most non-trivial part of the story, right? So essentially, this equation here, if you solve this, you have solved completely the problem. And what our approach allows us to say, to give information about solutions solving all these conditions and this box, I refer to this box equation here, without actually solving it, right? And this is done by what I sometimes refer as extremization, a geometric extremization approach, and it means that instead of solving the full equations, we want to extremize an object which is in practice becomes much simpler to handle, and one can then even write explicit formula which become just functions, not any more functionals. So the key object here is the supersymmetric action, which I write as I denote as S SUSY, and here is an expression. So here I switch gear, And I introduced this notation where if n is equal to 3, then we are in the type 2b case, and if n is equal to 4, we are in the 11-dimensional supergravity case. Okay, so from the purely geometric point of view, say for a geometer which does not care about string theory or black holes, that would be the way to study that, right? So you can take any n, in fact any n, even 27 or whatever you want, which is not relevant for string theory, but it's relevant for the geometry, right? So you can carry on this now the discussion with arbitrary n. Now, an important information is that this function here, this functional here, in fact depends, one can show that it depends only on the Killing vector, which I mentioned, and on the Kähler class of the transverse Kähler space. Okay, so that's the first important point to record. And for a supersymmetric solution, then we require that this action here is extremized. With respect to the vector. Well, you could ask why, and it's a good question. And one way to understand where this action comes from, you can regard it, for example, as the reduction of the full 10-dimensional action, for example, restricted on these particular solutions, or alternatively, but it's a kind of a circle. You can also regard this as an effective action which encodes the integrability condition of the Killing spinors. Again, I'm happy to give you more detail if you want. If you don't care, that's a kind of magical action that you take and you have to extremize. And most of the subsequent discussion will be how do I do that? I mean, how do I take this integral, which in principle it's not clear what to do with, and turn it into a function that I can extremize even a kind of a school high school pupil can do. All right, so in addition to the extremization, you have to accompany also with other conditions. The second one is the geometric version, so the implementation of the Planck quantization condition, which I said earlier. So this is a purely physical thing that we have to do. And then there is an additional constraint, which comes from integrating this equation here, right? You integrate this equation on the manifold. On the left-hand side, you get 0. So the right-hand side, after some manipulation, gets you to this equation here. So that's the full set, the full set of equation. The system will always contain extremization of S SUSY, this constraint, and then a bunch of other constraints, as many as the cycles of the internal geometry. Let me check the time. Okay, how I'm doing? I'm not doing very well, but anyway. Okay, so this means that we then obtain at once the dual of the C extremization for type 2b, right? So we have an object that we have to extremize, and at the critical point we'll actually give on the nose the central charge of the dual two-dimensional theory. And in the other context of M2 branes, when you extremize this SUSY action with the factor, with the prefactor, then at the critical point you get on the nose the entropy of the dual solution. Now, for solutions which were interpreted as wrapping a two-dimensional, say, Riemann surface, then the space always has the form of a fiber which we take to be Sasakian, and then the base, which is the Riemann surface. And importantly, the Killing vector, so this asymmetric Killing vector psi, does not mix with the Riemann surface, right? There is no U1 there, so you can't mix. So the whole point of this new paper, which is quite long, so you could say, well, it takes so long to do that, but it's kind of a technically complicated thing to do, is to replace now the Riemann surface with the spindle, and that leads to a number of complications. Perhaps the most important one to mention is that the spindle has a U1 symmetry, right? So rotating along the axis that goes to the north and south pole, and therefore you can have this mixing. And moreover, if we do it for the spindle, then we can hide, I mean, kind of naturally, this block structure of the entropy function will come out. So the entropy function, I can anticipate that, will be, it's essentially this S SUSY, right? So what we want to show is that if we have a solution of this type, where the base is the spindle, then this takes this block formula, right? So we want to take now, as I said, solutions where the base is the spindle, and in this case we can have mixing. And what we will find is that then there is a kind of localization that happens in the geometry. The full contribution of this S SUSY, which will be our entropy function, comes from the north and south pole of the spindle. So it's a kind of localization, but happens in the geometry. So it's a kind of old-fashioned localization. It's not the quantum field theory localization that we talk about more recently. Okay. So, and then the final step will be to specialize a bit more. So far, this is very general, but we specialize the fiber to be something a bit more concrete. For example, we assume that they have a toric action, then we can give very explicit expressions. Right, so we can start off by, as I said, assuming almost nothing. So we can assume that there are a number of U1 isometries, and this one on the fiber, and these U1 isometries don't have to be the maximal ones, as I said. So we assemble the full Killing vector. So there will be a part which is from B1 to BS, which is the U1 of the fiber, and then B0 denotes the U1 of the spindle. Right, B0 is the U1 of the spindle. So the full thing becomes then a vector which can point a bit on the fiber and a bit on the base, which is the spindle. And the main result, and I will definitely not attempt to prove it because it takes it's quite complicated technically, but intuitively what we get can be understood exactly from the point of view of this decomposition. So we get that S SUSY assumes exactly this factorized form. So a priori this wasn't clear at all, but it has this form of two building blocks. And the building blocks are what we in previous papers we called master volumes, and that's exactly the definition of the master volumes, right? So these are basically the volumes of the fiber evaluated in the North Pole minus the volume of the other fiber evaluated at the South Pole, and the plus and minus subscripts. It essentially means that these volumes now depend on some shifted variables. They don't depend on the usual variables that we have when we don't wrap on the spindle, but there are some shifted variables which I want to discuss a bit, right? So the shifted variable here I denote as psi plus minus and j plus minus. So they are respectively the kind of projection of the Killing vector on the two fibers at the North and South Pole, and on the Kähler class of the fiber again at the North and South Pole. Right. So whenever there is a plus, conventionally it corresponds to stuff at the North Pole, and whenever there is a minus, is stuff at the South Pole. Okay, so that's the very general kind of block decomposition, and then we can make this a little bit more. I still have, I guess, some 15 minutes or something. Yep. So we can make this more concrete in order to obtain, as I said, operative formulas. By operative, I mean formula that we can actually then extremize and eventually find the entropy or the central charge if we are in type 2b. So that we can do in two classes where in addition to the supersymmetry, which is the only thing we assume so far, we make some other assumptions. So this we can regard this as technical assumptions that allow us to make further progress. And I refer to the first case as Mesonic twist. I'll explain what it means. And then the second case, it's the toric case. Of course, there are cases which are familiar, such as spheres, which belong to both. So the spheres are toric, as you probably might know, but I will show you that also they belong also to this first so-called Mesonic twist. So the two cases also have an intersection. Okay, let's begin for this Mesonic twist case, and okay, so that's perhaps not very physical, but it's kind of clear from the geometrical point of view. So if we assume that the Kähler class is just proportional to the same to the Transmedial class of the GK geometry, then we have, sorry, rho was the Ricci form. then this means that yeah, the transverse class of the GK geometry restricted to the fiber is proportional to this, right? So perhaps it's more clear, in fact, if we make this a little bit more specific. If you are in the case where suppose that your internal manifold doesn't have any 5 cycle, say in 7 dimension, so there is no 2 cohomology, right? That's the case of spheres, for example, right? So there are no cycles. If you have a sphere, there are no cycles, and these cycles, they lead to additional U1s, which well, if you know it, they call it baryonic symmetries in the dual field theories. So they come from reducing on these cycles, and you get additional symmetries which are called baryonic, right? So essentially, you can think of this Mesonic twist case as a technical generalization of the case where you don't have any baryonic symmetry, right? Basically, you're treating the case where you might have baryonic symmetry in the same way as when you don't have, but this still leads to, I mean, still there is a very large class that enters in this case. Then we can make further progress, and we can essentially evaluate all of these formula. Okay, let me just flash the formulas again. So the recipe involves evaluating S-SUSY, then extremize it, and then evaluating this integral of the box equation and these fluxes. So all these formulas which are abstract become concrete. And in this case, for example, the S-SUSY then reads in this way. So for the 3 branes, S-SUSY becomes the difference of the inverse volumes of the internal fibers evaluated at the north and south poles. And for them 2 branes, instead there is a square root which appears, becomes the difference of the inverse square root of the volumes. And yeah, the volumes are just the Sasakian volumes, so those are say what we were able to calculate already from previous previous papers. And let me also tell you what are the B plus and B minus, which are again now become very concrete. So these projections, B plus and B minus, are written here. They are concrete formulas. We don't have to follow the details, but the formula involve the B of the fiber, the B0, which is the coefficient of the mixing, say with the spindle, and then the toric data, this kind of toric data of the fiber. Okay, so if we write this in terms of field theory variables or notation, then this entropy well, let's say, let me talk about here the entropy function, this curly S, it's 1 over B0, and then this difference of free energies evaluated at the one pole and at the other pole. Now, if you take this formula here, which I'm trying to highlight in blue, I don't know if you can see it, then this formula here, which is proved now, it's a mathematical proof, is exactly the same formula that we conjectured here in general. So it's exactly this formula here for the specific case of M2 branes, and the other formula is the case of the 3 branes. Okay, so here we have a proof of this factorization formula, of this block formula for M2 branes and the 3 branes in this context of supersymmetric solutions of GK type. Okay, what I want to say is that actually these are more general than this previous formula. Okay, so I already flagged that earlier. Those formula were relevant for solutions which are dual to spheres. So essentially, n equal 4 supergravity mills and ABJM. But these formulas here, you can take the internal geometry, the fibers, to be anything you want. Okay, so they are very general, right? So this, if you want, this is a very general prediction, because in the field theory we are, I mean, light years away, I mean, so to speak, from this case here, this formula here. We should do a localization of the field theory in general, large n, etc. Okay, so these are generalizations, and you can see I haven't written any explicit metric, right? So the only thing I need is this topological data for the fibers. Okay, so in the last 10 minutes, I want to talk about the toric case, which is the richest and the more interesting and also perhaps the clearest, because it becomes more concrete, even more concrete than the previous case. Okay, so this requires a bit of background, but I can try to squeeze in everything in the 10 minutes. So now, okay, the full internal geometry has a fiber which is toric, right? So now it has the number of U1s, which I denoted as earlier, is equal to n, right? So for example, is if the fiber is 5-dimensional, then there will be 3 U1s, right? It's toric in this case. Therefore, if you have a toric fiber and the toric base, the full guy, the full variety Y is toric. Okay, so we are in the situation with everything is toric. So the spindle has U1 symmetry, so the total space is toric and the fiber is toric. And the idea is to relate the toric data of the fiber to the toric data of the full space. Okay, and that will essentially lead us to our factorization formula. So there is some nice toric geometry behind this. Right, the toric data of the total space, which I denote Y, is obtained by adding to the toric data of the fiber, which I denote X, 2 extra points. Right, so suppose that your data lies in this plane, as you can see here. So that's in the plane you have the toric data of the fiber, and then the total space now, of course, has an extra dimension, and that's the orthogonal direction. And the spindle has only two points. Okay, so this point, which is here in the top and in the bottom, this is also called in mathematics a suspension. Right? So the toric diagram of the total space is a suspension of the toric diagram of the fiber. Okay, so basically, again, from earlier results for 3 or 4 years ago, where we could do all the toric stuff for the fibers, now we have just to supplement it with the extra points, and we got now toric data for the full space. The Kähler class also, in this toric case, can be decomposed explicitly in terms of the basis of, say, of the second cohomology, and then these Kähler coefficients, Kähler parameters, lambda A of the fiber. Again, there are explicit expression. So what I earlier referred to as J plus minus was a bit abstract, because I was telling you these J plus minus are Kähler classes at the North Pole and the South Pole, and then probably all of you would say, what do you mean? I don't understand it. Well, I'm telling you, in the toric case, there are these explicit expressions. They're just the Kähler classes lambdas of the fiber, shifted by this explicit expression here, which depends on this vector, and the master volume V plus and V minus. In this case, depends on these shifted vectors, which I already wrote earlier, and on these shifted Kähler classes. Okay, so then at this point, all that remains to do is you pick your favorite example, and in previous literature we gave formula for the master volumes. We have just to take those formula and plug in these values here. So as you can see, everything becomes algebraic. There is no any more differential equation. There is no PDEs or ODEs. You have just to solve some algebraic system. And here it is. So the problem turns completely algebraic, and it's summarized in these lines here. So you have to, well, partly summarize. So here you have the flux quantization condition, which are some expression that you can compute, and then you see the constraint also appear here. So once you have an expression for the master volume, which is a bit unwieldy case by case, because it can take several lines. You know, it becomes a bit complicated, but you can put it in Mathematica and compute it in you know, in an hour or so. And for any toric data, you obtain this master's volume, and then you plug in these formulas, and they're just algebraic equations, which in principle can always be solved. In practice, of course, you know, even Mathematica in practice often struggles or gets stuck, but that's a technical feature. Is, I mean, in principle, the problem is solved. Let me show you one nice formula which we obtain by manipulating further the previous formula. So in the case, this is very clear in the case of the three branes. So we obtain this general formula for S SUSY, which I also denote Z for the three branes, and the formula contains the following object. It contains these 3x3 determinants of the toric data, and these R charges. And these R charges, again, you can define geometrically, and these R charges are again evaluated in these shifted variables. Now, the point I want to emphasize, even for the non-expert, is that this formula, which we proved completely rigorously in the geometry, agrees precisely with the computation of the anomaly polynomial that in this paper Hosseini, Christoph, and Zaffaroni have done. So you take an arbitrary field theory in 4 dimensions, you compactify it on a spindle, and then you get this formula here, right? What I'm telling you is that you take a dual geometry, which is ADS3, and some internal geometry, which is a 5-dimensional fibered over the spindle, and you obtain exactly the same formula. So this kills, in a way, the kind of this problem, in the sense that it's completely solved, right? So for there isn't much more to do, in fact, for the case of ADS3 at this point, because you have a general matching. You don't have to, I mean, it's pointless to check any more examples. The situation is not as very well understood in the case of M2 branes, and there are things that can be improved there for the case of M2 branes. So let me summarize. So there have been 2 sets of developments in holography. Well, as far as my work is concerned, of course, there are many more developments, but 2, I think, interesting sets of developments on which I've been involved. One is this geometric extremization formalism, which formulates some extremal problem in the context of GK geometry, and in general, it leads to tools which are quite powerful for holography, because it allows to address many situations where it's impossible to find explicit solutions. And so far, a parallel, I mean, this joint development, we have found, people have found supergravity solutions which correspond to branes wrapped on spindles, and in fact, even more general orbifold recently in higher dimensions. With a neat holographic interpretation. So this recent, by recent I mean upcoming work, synthesize these 2 developments together and leads to we can see as the proof of the gravitational block formulas as kind of the final, or the main result, if you want. Along the way, there are many nice things, but if I want to give one, if I have time to flash only one formula, I will flash the formula where I show that S SUSY is the sum of 2 contributions at the northern south pole. Okay, so so this gave a very general proof of matching between gravity solutions and field theories. In particular, I'm referring to this formula here that I'm flashing. But also, and that's the part which remains to be explored more. We start that in the work, but there will be more things to do. Our formula gives access to the entropy of a huge class of accelerating black holes in ADS4, well beyond those that exist, and well beyond those that conceivably we will ever be able to construct in explicit form. Okay, so this poses very interesting question. Of course, well, from my point of view, perhaps the most interesting question is about field theory and localization on the spindle. And I have ongoing project of that. Well, the summer vacation didn't help in concluding projects, but hopefully with the with the end of the summer, we will go back in track. Thank you very much.